This is the gentleman standing above this pool of mercury, and he's holding his cannonball. Now remember we said that the density of mercury was about 13.5 grams per cubic centimeter, and iron was about 7.8, so iron is less dense. When this guy takes and drops the cannonball into the mercury, you see it floats so nicely. Once again, the thing that is the least dense will float on the thing that is more dense. That's why a helium balloon with a very low density will float in air. Air has a higher density than helium. All right, let's just quickly review what we said last week about the metric system. Remember, the International System of Units, SI units, defines length as its standard, and that is a meter, abbreviated as an M. Mass, the standard, is defined as a kilogram, and volume a cubic meter. We take in the metric system and we place multipliers in front of the standard units in order to get the unit we want to work with. We do this with a set of prefixes. P for pico, N for nano. This is the Greek symbol mu. Mu is micro, 10 to the minus 6. Milli, centi, deci, kilo, mega, and giga. When you put any of these prefixes in front of a metric unit, what you're doing is essentially putting in this multiplier. So if we were dealing with milli, and we wrote millimeter, the first M is this guy, and it refers to 10 to the minus 3. Therefore, a millimeter is 1 times 10 to the minus 3 meter. Now we can do this with all of our prefixes. Again, it is simply a multiplier and then whatever fundamental units you're using. We said we were going to use these in terms of ratios. The ratios we were going to set up based on the previous table for interconverting different metric measurements. For example, millimeter and meter are related by these. As we just saw, milli stands for 10 to the minus 3. So 10 to the third times 10 to the minus 3 is 1. Likewise, this one is even simpler. 10 to the minus 3 times meter is the same as millimeter. 10 to the minus 3, whatever. You can flip the ratios upside down. You can do that because they're all equal to 1. So you can invert them anytime you like. What we did with these ratios is we use them in a simple problem-solving algorithm. Problem-solving algorithm. You look at the word problem. You try to define what number is given. Then you figure out the ratio that's going to relate the given number and what it is that you're trying to find. The ratio is going to be one of these metric units that we just did. Although this is general enough, you can use it all the way through all of your chemistry. It's a very general algorithm. For example, if we were given meters and we wanted to find kilometers, our ratio would have to contain both of those. We know that kilo, from our table, is 10 to the third. So kilometer, kilo, meter, 10 to the third meter. That would be the ratio that we would use. Let's look at a quick problem. If we were given kilometers, as we just were, and we wanted meters, we would look at the problem here and say the thing that we're given is kilometers. The thing that we're trying to find is meters. We want a ratio that relates these two. So, our given here is our 6,000 kilometers. We can write 4 different ratios. Only rule on the ratio is that whatever units you have here for given kilometer here must appear in the denominator of that ratio. Here I've written 2 of them. Again, our unit must appear in the denominator. So to do our problem, we start off with our given. The ratio we want has got to be this one because the unit of given must be in the denominator. And we do this because now kilometers will cancel top and bottom. We're left only with meter, which is what we were trying to find. Do the simple math. 6.023 times 10 to the 6th meters. Any questions? Now we took the method and we elaborated it just a little bit. We said if you require more than one conversion, all you have to do is stick in more and more ratios. For example, millimeters to micrometers. There is no one simple ratio that's going to do that. So the easiest way to do this is to say, okay, I'm going to go from millimeters to meters, because I can do that. Then I'm going to go from meter to micrometer. So I need 2 ratios to do this. Start off with our given. First ratio has to be millimeters to meters. We know that milli is 10 to the minus 3. 1,000 times that is 1. Micro is 10 to the minus 6. We could say 10 to the minus 6 meters is the same as 1 micrometer. Write our given. Our first ratio must have millimeter in the denominator. Well, here I've written it in the numerator, but remember, because it's 1, I can just flip it over. Now we're set up so that millimeters will cancel. There they go. And now this whole lump is our new given. And it has units of meters. So our second ratio must have meter in the denominator. Well, this does, that's good. So we can just stick it in, cancel our 2 meters, and the only unit we have left is micrometer. Once again, the simple math. 1.6 times 10 to the minus 7 divided by 10 to the 3rd divided by 10 to the minus 6. 1.6 times 10 to the minus 4 micrometers. Now the one thing that I always tell my class, always, you are going to see these types of chain calculations. Everybody has their own calculator. Everybody's calculator is different. They all have different logic with brackets or no brackets or whatever. These problems you need to make sure you can do on the calculator you're going to use on the exam. Because otherwise, you're going to get lost. So make sure you do these types of things. Practice these chain calculations on your calculator. Any questions? All right, well, the next slide is a substitute for the one that was in there, so you're going to have to just write all over the side. Doesn't matter. But it's a simple set of conversions. I just put the wrong one in, I'm sorry. Go ahead and set up ratios to do each of these simple conversions. We'll talk about them in just a moment. You can also pull out your calculator and do the calculation. Once again, make sure that you know how to do this with your calculator. By dual table of prefixes, and you figure out kilo and gram. Kilos into the third. On an exam, I would refer to these mentally as 30-second problems. So in a typical exam that I would give, a problem like this, I would estimate it would take an average student 30 seconds to do it. Well, that's about how adept you should be at these sorts of simple conversions. Our first one here, we want to go grams to kilogram. Our given is grams, right? We know that kilo, K, is 10 to the third. We must set up a ratio that has grams in our denominator and kilograms in our numerator. One of the ratios that will work is this. 1 kilogram is the same as 10 to the third grams. So all you have to do here is simply multiply 2,000 grams by this ratio. So you're basically taking 2,000, dividing it by 1,000, and you wind up with 2.057 kilograms. The ratio must connect what you're given and what you're trying to find. Everyone happy with this one? Our next one here, we're going to do meters and micrometers. We remember micro, the Greek symbol mu, is 10 to the minus 6. So 1 meter is the same as, 1 meter is the same as 10 to the minus, is 10 to the 6th micrometers. Sorry, I'm saying that wrong. But we need meter in our denominator. So one of the 4 ratios we could use is this one. Micro is 10 to the minus 6, isn't it? So micrometer is the same as writing 10 to the minus 6 meters. Meters will cancel. You'll take 1.25 times 10 to the minus 7 divided by 1 times 10 to the minus 6, and you should get 0.125 microliters. Now, you could write this 1.25 times 10 to the minus 1. That's fine. Or you could use a decimal. Either one works fine. Do you have the handouts from the other week? Just in case you forget. Chapter 3 is not halfway through. Once again, your ratio must relate your given and what you're trying to find. Our next one, grams and nanograms. Nano, we kind of remember as 10 to the minus 9. It sounds like nano, doesn't it? So the ratio we want is going to relate grams and nanograms. We have to write the ratio so that gram is in our denominator. One of them that works is just this. Once again, just look at the logic. Nano, the abbreviation that is prefixed N, stands for 10 to the minus 9, doesn't it? So this is the same as 10 to the minus 9 grams. Grams will cancel, and you should take 9.3 times 10 to the minus 4 and divide it by 1 times 10 to the minus 9. Try it with your calculator. You should get 9.3 times 10 to the 5th.
Can you say it one more time?
Sure. We are relating grams, that's our given, and nanograms, that's what we're trying to find. So we need a ratio to relate those two. We remember that nano is 10 to the minus 9. Gram has to be in our denominator. So we write the ratio. 1 nanogram is the same as 10 to the minus 9 grams. And then the simple math, just multiply your given by the ratio. Kilo, what's kilo? It's 10 to the 3rd, isn't it? So, 1 kilometer is the same as 10 to the 3rd meters. We have our given here, 6.58 times 10 to the 4th. The ratio must be meters and kilometers, with meter in the denominator. We know that kilo is 1,000, right? Therefore, 1 kilometer is the same as 1,000 meters. K is just shorthand for 10 to the 3rd. And your simple math. 6.58 times 10 to the 4th divided by 10 to the 3rd. 65.8. Finally, grams and milligrams. Milli. We remember this now. Milli is 10 to the minus 3, isn't it? So our ratio must have grams in the denominator. Milli is 10 to the minus 3. 1 milligram is the same as 10 to the minus 3 grams. The little m, milli, is just shorthand for 10 to the minus 3. When we do the math, grams and grams will cancel. 2.78 times 10 to the minus 1 divided by 10 to the minus 3, 278 milligrams. Again, you could do this in scientific notation of 2.78 times 10 squared. Any answer works. Any questions? Make sure you get the concept here of taking your given, you find, you just need the ratio here, don't you? All you need to do in your ratio is remember what the prefix stands for and stick it in. Everyone good? All right, the next thing we talked about in this chapter was density. Density is a fairly simple subject. It simply relates mass and volume. The mass that we typically use, now again, you can use any mass and any volume. That works. Any mass and any volume. Most things will have their density quoted in grams per cubic centimeter. Now remember, a cubic centimeter, it's this little cube here, 1 centimeter on a side. Get the volume, multiply 1 by 1 by 1, and you get cubic centimeters. In chemistry, we will also use, in addition to cubic centimeters, we will use milliliters. The L here really is uppercase. 1 milliliter is exactly equal to 1 cubic centimeter. If you take 1,000 milliliters, again, milli, 10 to the minus 3. If you take 1,000 milliliters, that is 1 liter. So for most of our volume measurements, especially with liquids, we're going to be dealing with liters. But just remember, 1 liter is 1,000 cubic centimeters. 1,000 milliliters or 1,000 cubic centimeters. All right, we had a bunch of tutorials that we did in class. If you're having difficulty at all with any of these, I strongly suggest go to Chemistry Online, find it, and work it. These are algorithmic. Every time you work one of these, you will get a different problem. It deals with simple mixtures. When you're speaking of matter, Chapter 3 is entitled Matter. You're really talking about things that have mass, occupy space, whatever. Those are referred to as a substance. Now, a substance can be an element, or it can be a combination of elements in what we'll call a compound. But it's only one. It's only one thing. Now, if we take two or more substances and we combine them, we get a mixture. Under mixtures, we're going to have two types of mixtures. We're going to have homogeneous and heterogeneous. Homogeneous. No matter what sample you pull out of your mixture, it will have exactly the same composition, just like homogenized milk. Whatever sample you take, it's a mixture, but it will always have the same composition. Heterogeneous won't. Heterogeneous is just a gross, ugly mixture. Classic, something like this. That's gravel. If I reach in here, down here, and take a handful, it will have a different composition than if I reached in up here. This is heterogeneous. You can look at it and you can see big rocks, little rocks, whatever. Homogeneous is always constant. Now, a homogeneous mixture, something like salt water, really is a mixture. You know that because you can separate it by physical means. If I sat down and I wanted to, I could carefully pick out all the brown rocks, all the black rocks, all the everything. Physical means. I can separate them. With a homogeneous mixture, you again use physical means, and you can separate the two. Classic here, we start off with salt water. We're going to heat it up. As we do, it boils. The salt doesn't boil, the salt just sits there, but the water vapor will go up, it'll condense in our condenser, and collect down here as pure water. When we're done, we're left with salt, pure salt here, and pure water here. The boiling process here is a physical process. We're just taking the water from the liquid phase to the gas phase, back to the liquid phase, but it's still water. Nothing has changed. Any questions? Now, I talked about pure substances. Remember, an element is the simplest form of matter. If we have a single element that contains only one type of atom, that is a pure substance. If we take two or more different atoms and we combine them, we can make a compound. This is methane. Methane is natural gas, swamp gas, whatever. One carbon atom and four hydrogens. All four hydrogens are always arranged around the carbon in exactly this same geometry. This is a compound. We can convert the compound back into elements, but not by simple physical means. We have to use chemical means to do that, because we have to break these bonds in order to get there. We'll see that that's going to be called a chemical change later on. If we have methane, it is a pure substance. It is one thing, but it contains two different elements. So let's look at some really simple examples here. This is a rock. You've probably seen one before. The question is a rock a pure substance? Well, you can look at it and say it's pure rock, but that would be naive. Simplest way is to take a rock, do a little thin micro slice, and look at it under a microscope. When you do that, you can see easily that it's an aggregate. It's all these little bits of stuff squeezed together and solidified. This is obviously heterogeneous, therefore the rock is a heterogeneous mixture. These are gold bars. Now they all look different, aren't they? Different sizes, different shapes, different weights. Is this a pure substance? Absolutely. Because if you look at this on the atomic level, these contain nothing but gold atoms. It is a single substance, a single element. Doesn't matter what it looks like, it is a single substance and it is pure. Ice water. Now this one kind of depends on your definitions here. We have ice, which is simply frozen water, right? And we have water, which is unfrozen water. So it's a liquid and a solid phase mixed together. Can we separate these by physical means? Absolutely. We can sit there and take out all our ice cubes. Now, if we do it slowly enough, they all melt, don't they? And we're all back to water. So, in its present state here, this is a heterogeneous mixture. But if we're really slow about getting it all out, it would melt to pure water, and that would be a pure substance. This is table salt. You may have looked at table salt under a microscope before. It's little tiny cubes. Now again, you look at these, they're all slightly different, aren't they? But salt, table salt, is a chemical compound. It contains only sodium and chlorine atoms. And they're arranged in these little cubic structures. That's actually why these are cubic crystals. So this is a pure substance. It contains the compound sodium chloride. All right, here's a list. Decide if these guys are pure substances, heterogeneous, homogeneous, or elements. Air. What is air? Air is mostly nitrogen, about 80%. Almost 20% oxygen. Then there's some CO2 thrown in, and a whole bunch of other stuff. But every sample of air that I take from here or here is going to be the same, isn't it? That means it is a homogeneous mixture of these gases. Now you take pepper and you put it in a grinder. What do you get? lots of little flecks. You get some light ones, some dark ones. You could sit there very, very carefully and separate them, couldn't you? It is therefore a heterogeneous mixture. Seawater, salt water, mostly water, but we have sodium chloride dissolved in it, also a lot of magnesium chloride, and other things. There's actually a lot of gold in seawater as well. But every sample that you take, assuming that you're just going here to here, is going to be the same. It is therefore a simple homogeneous mixture. Sugar. What is sugar? Sugar is sweet. Sugar is actually a simple compound. This is sucrose, table sugar. In this little ball and stick thing here, the carbons are shown as black, oxygens are red, hydrogens are white. Every sugar molecule has exactly the same structure. It is a pure substance. Contains carbon, hydrogen, and oxygen, 3 different elements, but they're always the same. Therefore, it is a pure substance. When we buy gasoline, you can buy different octane ratings. What is octane? Well, octane is a hydrocarbon. It's lower boiling, burns faster and better. That's why in high-performance engines you want something like that. But from the pump, all gasoline samples are going to be the same for the same octane. Therefore, it is homogeneous mixture. And finally, gravel. Well, gravel is simple. Gravel is just a bunch of little rocks we've already seen. We can pick them out. This is heterogeneous. Any questions? Simple concept. Just think, can I separate it by physical means? If you can, it's a mixture. All right, let's talk about physical properties. Physical properties. Physical properties are things like, well, what something looks like, what it smells like, what it feels like, whether you can bend it, how hard it is. Very physical things that appearance-based, if you will. This is an interesting little picture. This obviously is ice crystals. This is water in the solid phase. As we said earlier when we were talking about the ice in the water, those are the same chemical compound, water, H2O, except in different physical states. The simplest physical property is going to be physical state, whether it's a solid, a liquid, or a gas. Now we're going to talk about the properties of each of these, and we're going to talk about why they are that way. This represents our solid. It's a lump. This represents liquid, and this represents gas. This little movie down here, we'll talk about why it is this way, but solids are defined in their shape simply because they're stuck. Liquids, very fluid, flowing around each other, and gases are just really hyperactive. Solids. Solids will have a defined shape and a defined volume. So we have a rock. The rock has a shape and the rock has a volume. It doesn't matter what container you put it in. It's still going to have the same shape and the same volume. Liquids, on the other hand, have a fixed volume, but whatever container you put it in, they will form to fit the container. The water in your water bottle goes to the shape of your water bottle. Gases have neither defined shape nor volume. They are just hyperactive little particles that are just buzzing around like mad. They take on the shape and the volume of your container. If you finish your water bottle, put the cap back on, it's full of air, isn't it? That air has the shape of that container and the volume of that container. Now we can do phase changes. If we start off with a solid, we can heat it up and it'll melt. Our ice cube melts into water. Likewise, we can take water, freeze it, and go back to ice. If we have a liquid, we can go to the gas phase, boil it. When we do that, we leave our liquid phase here. These things now are free molecules flying around. If we cool it off, we can go back to our liquid. Each of these transitions, the melting, the boiling, are associated with a unique temperature for a given substance. That's referred to as the melting point and the boiling point. And that's one of the physical properties of a substance. Where does it melt? Where does it boil? There's one other that you might see in general chemistry. Typically they don't do this in intro, but sublimation, you can actually go directly from a solid to a gas, and you can go back again. Back in the old days, you used to be able to get iodine in the drugstore, actually. And there would always be a bunch of crystals of iodine on the top of the bottle. That's simple sublimation, leaves the solid state into the gas, condenses out, etc. All right, let's just do a couple very simple state questions here. This is bromine. Bromine is Br2. This is it on the periodic table. Bromine, this particular substance, melts at -7.2 degrees centigrade, and it boils at 58.8 degrees centigrade. This little vial here contains some bromine. It was frozen, so this down here is still solid bromine. As it melts, it forms this little glob, and as it does, we have bromine gas in the gas phase. Bromine is very toxic, so don't do this at home. All right, if I tell you, or I ask you, we're at -20 degrees, what is the physical state of bromine? All right. If we were above the melting point here, let's say we were at 0, it would have melted, right? So if we start at -7 and go up to 0, we're putting energy in and it melts. If we go up above 58, it'll be the gas. This is below our freezing point, isn't it? Because it's below the melting point, this will be a solid. Melting point, freezing point, same thing. If we take a bromine and heat it up to 80 degrees, what happens? That's it, we're above the boiling point, aren't we? If we're above the boiling point, it's left the liquid into the gas. And finally, if we were at minus 0.12, well, that's less than the melting or boiling point, isn't it? But it's more than the melting point. So this is a liquid. Simple question here. If we have a pure substance that is 15 degrees above its boiling point, what is it? If you have difficulty with the concept at all, think about temperatures in terms of a number line. Even without numbers, we have solid, liquid, and gas, right? This is our boiling point, that's our melting point. We're 15 degrees above. If we're above it, we're in here somewhere. Therefore, it's a gas. A compound melts at 115, boils at 325. We're at room temperature, which is about 25 centigrade. What is it? Think about your number line. But now we have numbers here. 115 is our melting point. That's from solid to liquid. 325 from liquid to gas. And we are 25. That means we are a solid. Let me do one more. I put in negative numbers here because that always confuses everybody. This stuff melts at minus 45, boils at minus 4. And we are sitting at minus 36. Same number line. Solid to liquid, minus 45. Liquid to gas, 4. And we are minus 36. We have a liquid. Any questions? All right, let's explain why all this is this way. We're going to introduce what's called the kinetic molecular theory. It's actually a very simple principle. Remember these little tiny buckyball magnets that you can't buy anymore because they kill kids and stuff like that? But they're little round magnets, aren't they? You can take them, they wad up into a little ball, and you can shape it any way you want. That's because they have an attractive force for each other. Well, it turns out that every particle in the universe has an attractive force for every other particle. In general chemistry, we will refer to this as intermolecular forces. Things just attract each other. And there's lots of mechanisms for how that happens. But, bottom line, they just attract each other. Just like these things shape up into a little ball because they have a magnetic force holding them together. All right, think of this as a solid. It's just sitting there as this little ball with its own shape, its own size, and its own volume. Now, kinetic molecular theory also tells us that nothing in nature is ever still. You have children, you know what I mean. Nothing in nature is ever still. But in a solid, these individual particles don't have enough energy to break these attractive forces. They can't break them. So they just kind of sit there and shake. They'd like to, but they can't. Not enough energy. Now, the force between a substance is unique for that substance. But if we take this now and we put energy into it, these guys are going to gain more energy, and at some point, they're suddenly going to be able to slip and slide all around each other. So they don't have enough energy to break the intermolecular forces, but they can slip and slide all they want. What we've done is gone from a solid to a liquid. Because these are slipping and sliding, this is going to take on whatever shape we have for a container. The energy it takes to do this depends upon the intermolecular forces, which are unique for every substance. That's why everything has a unique melting point. Finally, if we take our liquid and we put in enough energy, we can totally overcome all of the intermolecular forces, and these little guys just fly around like mad until they hit the walls of the container. That is, they fully occupy the container, they do the shape of the container, and they do the volume. That is solid, liquid, and gas. That's pretty simple, isn't it? Let's just recap. A gas. Particles are highly separated, aren't they? They're just flying away. That's why you can take a gas and compress it. You can also put it in a bigger container and it will just expand because it goes so it hits the walls. A liquid. They're still packed closely together, so they have a defined volume, but they take on the shape of their container because they're slipping and sliding around. And finally, a solid. Solid as a rock, fixed positions, defined volume, and nothing else happens. All right, transition between solid, liquid, and gas is a classic physical change. So we're going to look at changes here. We're going to look at changes in properties. We've already said a physical property is basically just appearance or its density is a physical property, inherent property of it. A chemical property, however, is different because a chemical property tells us how this is going to act in combination with another substance. If we take one substance and another substance, and we put them together and say add heat or whatever, something happens. You light a match, something happens. You wind up with something that is a different substance. That's a chemical change. We convert one material into something else. Physical change, still the same stuff, just in a different form. Classic example here. This is aluminum, a little wad of aluminum foil, and we've already met bromine. both of these are elements. Each of these contain only one type of atom. If we take bromine and aluminum and we mix them together, they're going to react. Now, this is a little beaker. This is some bromine in the bottom. And this is a little beaker here with aluminum in it. If we take, oh my gosh, it's not going to do it. These were all working so nicely. Let me just see if I can force it to do it. Yes, I forced it. So what this guy is doing is he's taking the aluminum and he's adding it to the bromine. Now just a little bit in there. After a minute or so, you see you get a really nice reaction, lots of heat. These are very, very toxic fumes. Again, don't do this at home. But when we're done, when it's all finished, if you look at the beaker, well, we started off with bromine, the brown liquid, aluminum, the metal. We have this white solid. This is aluminum bromide. We have taken two substances, we've done a reaction, and we've made a new substance. This has totally different physical properties and chemical properties than these guys did. This is a chemical change. Because it's a chemical change, this is what we'll define as a chemical reaction. A reaction, you start with reactants. These guys go to products. This guy, when you do the chapter on reactions, you'll see that the chemical arrow here has the same properties as an equal sign. So the mass and the number of atoms here must equal the mass and the number of atoms here. But that's another chapter. Classic chemical change. Once again, a classic physical change. We have an icicle. As it melts, it drips. This is water, though, isn't it? And the drips are also water. Physical change. Nothing happened. But if we take water and put it in a little electrolysis device, pass an electric current one side to the other, we take water, H2O, and we can break it down into oxygen and hydrogen. These have different physical and chemical properties than this. This is a chemical change. We have taken a substance and made new substances out of it. See the difference? Any questions? Look at these and just very quickly classify them. Fortunately, we're not to the point where frost is forming yet, but it feels like it's going to come. When frost forms, what do? You take water from the gas phase and convert it directly into the solid phase. That's what frost is. But it's still water, isn't it? This is a simple physical change. Now this next one is actually extremely complicated. But if we start off with a corn, I taught biochemistry for years and years, but so you start off with a single kernel of corn, you grow a corn stalk, right? And then you eat it and the cycle continues. The corn stalk that we wind up with is totally different than what we started with, right? This is actually, a huge number of chemical changes happening as the thing undergoes this biological transformation. And the neat thing about biochemistry, if it's taught right, is that you can appreciate the chemistry in each of these steps. That's the neat thing about biochemistry. We light a match. Well, the match has phosphorus in it, an element. Reacts with oxygen in the air. We get gases, we get a burned matchstick. These are all chemical changes. Totally different properties than what we started with. You sweat, therefore you are. And then eventually you dry off. Still, that's just water evaporating off. Simple physical process. And now nobody knows this anymore because nobody uses silver forks. But if you have real silver and just kind of leave it out somewhere, it tarnishes. Maybe you have jewelry or something that does that. It's not coated. Why is that? Turns out that the tarnish is silver sulfide. And there's enough hydrogen sulfide in the air that it can react with the silver surface and form this compound, Ag2S. So this is actually a chemical reaction. Silver reacting to form silver sulfide. All right. We talked about chemical reactions. Remember, a chemical reaction, just like aluminum plus bromine, describes a chemical change. And like we said, we can represent this with an equation, reactants linked to products. An example of a chemical reaction is kind of a fun thing that we used to be able to do in lab. We can't do them anymore, but they were fun. There are metals in the periodic table. These guys in the first group. These react with water instantly, as soon as they touch. Potassium is one of those. If you take solid potassium and water, add them together, you will form potassium hydroxide and hydrogen gas. Now in reality, this thing gets so hot, just like the aluminum and bromine, this hydrogen gas spontaneously reacts with oxygen and burns. So it's kind of a really neat, fun thing to do. If you notice this equation, remember I said the chemical equation must have the same numbers and types of atoms on both sides. Here we have 2 potassiums, 2 potassiums. We have 4 hydrogens, 1, 2, 3, 4 hydrogens. 2 oxygens, 2 oxygens. Chemical equations must have same numbers and types on both sides. Let's look at this. This is potassium. Now it's stored under oil to keep it away from the air. This is water. Now I hope this one works. By gosh, it's not going to work for me, is it? I don't know why. it goes. All right, so this guy reaches in, pulls out this little chunk of potassium. It hits. As soon as it does, it melts. That's why it runs around in this little glob. Hydrogen gas reacts with oxygen, and it burns. That was so much fun. Let's see if it'll do it again. It won't. Hydrogen gas is produced and burns. If you do this with a great big chunk of it, it actually does quite a sizable explosion. Another reaction. We just saw hydrogen react with oxygen and burn. We have 4 hydrogens here, 4 hydrogens here. 2 oxygens, 2 oxygens. It's a balanced equation. Now, this is a balloon filled with hydrogen. This is a room filled with air, oxygen. And this is a very brave person with a lighter on a stick. Now that is fun. You got to admit that. Any questions? All of these are obviously chemical changes. The water, different in every respect than the hydrogen and oxygen that you start with. Let's do another set. Identify these as physical or chemical changes. Gold leaf. If you take gold, gold has the unique physical property of being the most malleable of all elements. You can actually take a chunk of gold and pound it down so it is literally just a couple atoms thick. It's amazing. You can take a gram of gold, so little tiny chunk, and you can actually hammer it out so thin that you get what's called gold leaf. When you see like a church or something like that with a big dome on it that's all covered with gold, you think, wow, that's a lot of gold. But it's not. It's just extremely thin gold leaf. Amazing. It's still gold though, isn't it? This is a simple physical change. If we heat water to boiling, we're going from the liquid phase to the gas phase, but it is still water. And finally, if we go home tonight and we barbecue, we take carbon, heat it up, we get carbon dioxide. That's a chemical change. So let's kind of summarize what we've said about matter. We start off with matter. Remember, matter is something that occupies space and has mass. We can define what we call a pure substance. Pure substance has only one type of matter. It can be an element, can be a compound, but it only has one. If we take pure substances and mix them together, We can get mixtures. And they can either be heterogeneous or homogeneous. You tell the difference because the sample you take here is always the same. The sample you take here is always different. But only by physical methods you can separate both of these back into pure substances. Pure substances can also be elements or compounds. Remember, an element contains only one type of atom. Compound will contain two or more types of atoms. We can convert compounds into elements, but can't do it by physical methods. We have to use chemical methods to break those bonds. Any questions? All right, well, let's end with Lavoisier. There's one last concept in the chapter here, and this is the conservation of mass. We've looked at reactions. We said we had the same numbers and types of atoms on both sides. Well, it goes one step further. You also have the same mass on both sides. The total mass of your reactants must equal the total mass of your products. Now, Lavoisier showed this way back in 1770, whatever, long time ago. This is the device he used. Basically, what he did was to take mercury, heat it up in oxygen to make mercury oxide. What he found was that he could take, very carefully weigh out his mercury, very carefully weigh the products, and in his closed apparatus, he could also weigh the oxygen. So, he knew the mass of what he started with, the mass of what he got. He could also take this, heat it back up, and convert it back to mercury and oxygen. Now, for the day, this was absolutely remarkable thinking. Lavoisier was the first chemist to do quantitative chemistry. And for that, it really is just an amazing concept. This is him and his 13-year-old wife. Those were different times. Unfortunately, as you can tell just by the way they look, Lavoisier was a French noble person. And this was at the time of the Revolution. He was an investor in a company like a stockholder, that was a tax collector for the king. And the Revolution judged him to be a criminal for having a wrong investment, and so they killed him. They chopped his head off. The judge at the trials said the famous quote, "The Republic needs neither scientists nor chemists." Maybe that's what's wrong with the French even today. All right, let's look at just a couple very simple multiple choice questions here. Which of the following represents a physical change? Lighting a match. Well, we've seen that. That burns. That's a chemical process, isn't it? Putting sugar in tea. The sugar dissolves in the tea, doesn't it? But you could remove the water and the tea and get your sugar back, couldn't you? So that's physical. Melting of aspirin. Yes, aspirin is a real chemical compound and it melts. That's a unique melting point. That's physical. B and C are the correct answers. Choose from the following those properties that are chemical properties of carbon. It's a solid at 25 degrees centigrade. That's its physical state, isn't it? That's not a chemical property, that's a physical property. It's insoluble in water. Well, sugar dissolves in water, but carbon doesn't. But nothing happens, it's still carbon, isn't it? It's soluble in carbon 10. Well, sugar is soluble in water, but it's still sugar and it's still water. Reacts with oxygen. Now you're cooking. That's a chemical reaction. It crystallizes to form diamonds. Well, charcoal and diamonds look differently, but they are still just carbon. D is the only correct answer. Which of the following statements is correct? Compounds cannot be decomposed into elements. Well, we know that's wrong because we saw the electrolysis apparatus, right? Where we took water and broke it down to hydrogen and oxygen. Elements and compounds are pure substances. Well, that sounds pretty good to me. Elements but not compounds are pure substances. Now, B is the only correct answer. Volume of a sample of magnesium weighing 5.68 grams is 3.36. Now, from that little bit of data, you can calculate the density, can't you? Now, we're going to take this magnesium and we're going to put it on a liquid. Think about our cannonball and mercury. The three liquids we're using have densities of 1.48, 1.59, and 2.5. Where will it float? What you have to do is calculate the density. 5.68 divided by 3.36. What is that? Somebody have a calculator? .68 divided by 3.36 is 1.69. So, it is less dense than the last one, but it's more dense than the first two. So this is the guy it will float on. We are given densities of cadmium, copper, and zinc. We have an unknown with a volume of 15 cubic centimeters and a mass of 133. What is it? It's one of those three. How do you calculate your density? You're going to need to know that in about 2 minutes. Mass divided by volume is density. Do the calculation. You get 8.92, which matches copper. And our last one here. Well, actually, there's one more after this. We have a balloon with helium. This is its density. The mass of the balloon is 2.225 grams. What's the volume of the balloon? Density is mass divided by volume, right? So solve the equation for volume. Mass divided by the volume, by the density, 12,500 cubic centimeters. Remember, 1,000 cubic centimeters is the same as 1 liter, so this is the correct answer. And our last one. Remember I said seawater contains table salt, sodium chloride, and magnesium. Turns out it contains a lot of magnesium. That's why sea salt has a slightly different taste. Seawater, here's its density, contains 1.41 grams of magnesium per kilogram. What mass of magnesium is contained in 16.5 liters? Now that sounds complicated, doesn't it? But it isn't. This is 16,500 milliliters, isn't it? Which is the same as 16,500 cubic centimeters. Now just doing a ballpark here, the density is about 1. So from this 16,500 cubic centimeters, about 16,500 grams. That's about 16.5 kilograms. Everyone is 1.4 grams. Our mass turns out actually to be 17 kilograms. Multiply by that, and you get the amount of magnesium. All right. Everyone take a deep breath. It is time for our quiz. Quiz, once again, is on Chapter 2. Please make sure you put your name on it. Oh, no. All of the other stuff that you have for me, just save it to Wednesday. Everything else will hang in on Wednesday, okay? Did I? But it's quiz time. You'll need a calculator, so make sure you get one out. It's very simple. Should be done with it in 30 seconds. Maybe 40. And remember, on Wednesday, we will do experiment number 3, dealing with density.